Hello everybody, my name is Edmond Adib. I have prepared this presentation as a part of my application to a PhD program. Um, Here I present an easy method for designing a control system which is applied to a fluid catalytic cracking unit, which is a unit in refineries which produces gasoline. In this slide, one of the most widely used configurations of FCC unit is shown. This particular configuration it's called the UOP side-by-side design. This is the reference that I used in this presentation. I took the mathematical model presented in this paper and used it for my simulations. It's a paper published by Popa and Patracio in Advances in Dynamical System and Control in 2010. A little bit about on what happens in this unit. An FCC unit majorly it consists of two major units, regenerator and reactor plus this integrator. Um, the feed is mixed with steam and also freshly regenerated catalyst and then sent to the riser. The riser is basically the main reactor, the heart of the process, where the main reaction, cracking reaction takes place. It's a plug flow reactor, gaseous phase. The residence time in this reactor is very, very short, in the order of seconds, maybe 3, 4, 5 seconds. At the end of the riser, there is a disintegrator which separates the spent catalyst from the products. The products is the hydrocarbon broken down into lighter molecules. It's sent to the fractionator. The spent catalyst, which is covered with the the coke, is sent to the regenerator. In the regenerator, it mixes with hot air, and the coke burns, produces CO2, which is another product of this process, and then sent to further processing and downstream units. And the regenerated catalyst is sent back to uh, to to the riser. Here in this slide, the input-output model is shown. The identified model has 5 inputs and 2 outputs, and also the interaction between variables are also shown in this diagram. The model is an identified model. It has been developed from step response of the system. As you see in this table, the mathematical relation between each input and each output is presented. There are 5 inputs: feedstock temperature, regenerated catalyst temperature, feedstock flow rate, regenerated catalyst flow rate, and also air flow rate to the regenerator. The outputs are riser outlet temperature, which is mainly the operating temperature of the reactor, and also regenerator temperature, which is controlled mainly by the airflow, and also other variables because there are some interactions. Um, the regenerator temperature indicates how the catalyst regeneration operates. Um, So as you see, the mathematical model is presented in frequency domain, and it is a matrix, basically 5 rows and 2 columns, a 5 by 2 matrix. This is the transfer matrix of the plant. Here in this slide, the block diagram of the plant is shown, and also the dimensions of the matrix, the plant matrix, and also input vector, also output vector are shown. This is the original form of the model. Um, so, yeah. The mathematical model presented in that paper is taken, and MATLAB is used to transform it into state space model. This is the matrix A. This particular realization is not minimal. As you see, those small numbers are very close to zeros. There are lots of zeros in this matrix. This is basically a sparse matrix. MATLAB is capable of producing a minimal realization with much less number of states. Of course, in the minimal realization, the matrix is not sparse anymore, and it has less number of zeros. So this is part of the matrix A of the non-minimal realization. The rest of matrix A and the rest of matrix A, and matrix B has 21 rows because we had 21 states, and also 5 columns because in the model there are 5 inputs. Matrix C has only 2 rows because there are only 2 outputs, regenerator temperature and reactor temperature, and it has 21 columns because there are 21 states. Matrix D is all zeros. From the 5 inputs that we had in the model, we picked 2 as disturbances. We treat them as disturbances and use the rest of them as manipulated variable to control the controlled variable. Um, to do this, we have to extract the corresponding rows and columns from the original matrices A, B, C, and D developed in the previous slides, and define a new set of matrices A, B, C, and D, and then use the function SS in MATLAB to convert the continuous model we got in previous slides into a discrete model. To do this, we use SS function once again to with a discrete with a sampling time t sub s, and the output of this function would be uh, the state space model, discrete state space model with 2 disturbances and 3 manipulated variables with 2 outputs. The reason that we do this, I mean, we take the number of this equal number of disturbances and control variables. The reason for that is that in MPC control, the control would be an offset free, and the reason is given in reference number 4. Here in this slide, the step response of the whole plant is shown. Basically, we apply a step input into each input, and the output of that particular output is plotted against time. Um, pretty much straightforward as other chemical units, first order lag, more or less. The only thing which is interesting here is an inverse response, which is seen in the diagram in the second row and the fourth column, um, which is between the input of catalyst flow rate and the output of regenerator temperature. So at first you see a drop in temperature and then it goes back up into the positive range. The reason for that is that two physical phenomenon is acting against each other. First, when you increase the catalyst flow rate uh, because of the shock of an increase of the mass within the reactor, the temperature drops. But as the time goes by, with the increase of the coke present in the reactor and the burning of that coke, the temperature goes back up in the positive regions. In this slide, gain and phase margin of the system, individual systems are investigated. Uh, as you see, there is no instability in the system, and there is no right half plane zero in the system. System behaves pretty much well behaved, um, and that's it. Now we come to the question which input should be used to control which output, which is called pairing strategy. There are some measures in the literature that can be used for pairing strategies. The most famous one is called relative gain array. It's calculated from the steady state matrix of the system in the frequency domain. The matrix in the frequency domain is used with s equal to 0. For this strategy, the criteria is that the individual element lambda should be positive, because negative lambda would lead to an instability in the system, and it should be close to 1. Large lambdas should be avoided as much as possible. Also, it's advised to plot relative gain arrays in the whole through the whole range of frequency, because there is a chance that lambdas change behavior in some frequencies. So to make sure that at all frequencies lambdas meet the criteria, it's advised to plot relative gain array in the whole range of frequency. And also there is a measure called Niederlinsky index. It's advised to, for each pairing, the Niederlinsky index calculated. It should be positive, otherwise again it leads to instability. There are some other measures in this area for comparing pairing strategies. These measures are mostly based on controllability and observability gradients. Namely, these measures are Hankel norm, Hankel singular value, and also Hankel interactions. Um, and also participation matrix. These are all based on Gramian's observability and controllability Gramians. Now that we have investigated our pairing strategies, now we come to the question of control strategies. There are several control strategies available. Um, One of them is decentralized control and using decoupler matrix to decouple the matrix and produce a diagonal matrix in the for the plant. In this case, we would have multiple independent sisal loops without any interaction because we have eliminated the interaction using the decoupler matrix because we had the model of the system. The other option is using model predictive control and also basically with model-based model-based predictive control. And also DMC matrix, DMC control, dynamic matrix control, which is a special case of MPC. And also the other approaches available is traditional feedback MIMO system. The main reference is the Skogestad method. So we have several options of for the control strategies. Okay, now we have several options of pairing strategies and also several options for control strategies. We have to investigate the combinations of all these options. Um, for each case study, we have to investigate the performance of the system in terms of the magnitude of overshoot, if the overshoot is acceptable, physically acceptable to us or not, or the rise time is enough or not, and also the response time is fast enough or not. The degree of oscillations we get, if any, we have to investigate that too. And also the parameter which is important is the variation in manipulated variable to get that control. If the manipulated variables, any of them is vary too vastly, it would involve some cost because the manipulated variable always involves some sort of cost, and also it might not be physically possible, and we can because in reality there are some saturation for the manipulated variable. Okay, so we have selected the best combination of pairing strategy and control strategy. Now we have to make sure that the system is operating always around at or around the operating point because the identified model has been developed uh, around that particular operating point. If the system is operating far enough from that particular operating point, the model might not be representing the the physical system, and there might be some mismatch between the model and the physical system. So if this happens, we have to re-identify the model, both in terms of the structure of the model and or the parameters of the model. For this, we have to put the system offline and apply a proper input or proper inputs, which means that the inputs should be rich enough to simulate all the modes of the system, all the hidden modes of the system, and collect the input-output data. These input-output data are fed to the identification system, and the new model is developed. So to do this, we have to put the system offline, which might not be um, always practical or economical. So idealistically, we are looking for an identification system, identification method to identify to be which is capable of identifying system when the system is in its normal operation uh, without needing a rich input, a particular input. So this is the ideal goal. We need an identification system which can identify the system without that particular uh, input. Uh, the same analysis that we did in this presentation can be applied to any other model. One of the models that I have in mind is the activated sludge model number one, ASM1. The ASM1 is much more complicated than the system that we saw today. Um, it's highly nonlinear and with 8 different processes, 13 different components, so 13 different material balances is required. Okay, that's it. This was how a control system design in industry is approached. I hope you enjoyed this presentation. Thank you. Have a good day.